Good evening, sir.
Yeah, good evening. Uh, okay, so we'll do magnetism. So this is basically chapter 34, 35, maybe one more chapter after that in your HCV book. So
Yeah, it's still 37.
yeah, how was your test on Sunday?
Like the physics and maths portions were okay. Physics was fine.
Hmm,
The chemistry part was bad, so the overall went down.
how much?
Uh, like I got 157.
Hmm.
In physics I had gotten 86, and in maths I had gotten around 70.
And in chemistry?
Chemistry I had gotten only 6. I did not understand the questions very well.
What happened? How is this possible? Like, what was the syllabus?
It was full syllabus, mains,
Hmm. So
but
what
yeah.
was the problem? Like, which portions of chemistry were bad? Like, you have the paper.
Yeah, I do have the paper. I think it was mostly equilibrium,
Hmm.
and then like organic was fine, but it was like equilibrium, and it was like long reactions. So I just messed up in middle, and then
After the exam, when you looked at the paper, how much is doable?
yeah, I think I could have done like at least 7 to 8 questions properly,
Hmm.
but I feel like at the moment I just lost entire faith in the paper, and I was like too scared to even think about anything.
No, but after the exam, forget about the paper. After the exam, out of the 25, 30 questions, you should still be able to solve 15, 20. No, that is the target. Like,
Yeah, I know, but the
so
like
there is a major problem in chemistry, or it's just one or two chapters which are bad.
no, it was like this was the first time I had actually messed up chemistry. Otherwise, usually it's fine.
Hmm.
And the average this time was also comparatively very low. For it was 33% for overall and 15% for chemistry.
Hmm. That's fine. Other subjects are fine, but chemistry you need to fix. If there is a problem, you need to fix it quickly, right?
Yeah, like I think it was mainly just the equilibrium part. So I started doing that again.
Hmm. From where are you doing? Allen book.
Yeah, the Allen lectures.
Okay. Let me know if there is some major problem. We can discuss those topics also. But I mean, you have to fix chemistry. It cannot be like that. No, it cannot be like one day your chemistry became six, right?
Yeah.
Uh, Anyway, magnetism. Basically, the first thing that we will learn is effect of magnetic field on charges. On charges, or basically force exerted by magnetic field on charges. That is your topic for chapter 34. So by experiments, people figured out that any magnetic field B will exert a force on a charge Q on Q, and that force will be Q V cross P, where V is the velocity of the charge, right?
Yeah.
Now, this is obtained by experiment. So people made a charge move, and then they saw that the charge changes its path. Therefore, some force must have been acting on it. And then when the velocity was reversed, the direction of motion of the charge also reversed. So if it was going like this, one time it might deviate like this, and one time if the velocity is reversed, it deviates like this. So basically, this deviation is happening because of some force that is acting in this direction or in this direction, right?
Yeah.
That force is because of the magnetic field. Now, there are several things to note here. One thing is that force that is exerted on a charge is going to be perpendicular to both velocity and the magnetic field. So basically, force, since it is perpendicular to velocity and magnetic field, this force cannot do any work, right?
Yeah.
Because work done is F dot ds, and if F is perpendicular to the velocity, then the angle between the force and the velocity is in the direction of ds. Therefore, the angle is 90. So cos will be 0, right?
Yeah.
If this magnetic force cannot do any work, then that means that it cannot change the kinetic energy of the moving charge. So basically the speed of the charge has to remain the same. Correct?
Yeah.
This is from work energy theorem. If work done by a force is 0, the net change in kinetic energy will be 0, right?
Yeah.
So kinetic energy of the moving charge remains the same. That means speed is the same. That means the only thing that is changing is the direction, right?
Yeah.
So direction of velocity changes if it is moving under the influence of a magnetic field. And because the direction is changing, you will still say that velocity is changing. Therefore, it has some acceleration. But the velocity is changing in such a way that the magnitude of velocity or speed remains constant, right?
Yeah.
So if it is moving at v like this here, when it is moving here, it will have some I cap and some j cap in such a way that v1 square plus v2 square will still be equal to v square, right?
Yeah.
So speed here will still be equal to speed here. The direction has changed. The other thing to realize here is that if obviously if the velocity is 0, the force on the magnetic field is 0, right?
Yeah.
Now, because of this force acting on a magnetic, on a charge, what happens is the body may move in a path like this. You will realize that at any point, the direction of acceleration will be perpendicular to the velocity, right?
Yeah.
If this is a force, this will cause some acceleration. That acceleration has to be perpendicular to the velocity direction, right? Because force is perpendicular to velocity, right?
Yeah.
So as a result of this, it might end up moving in a circular path because every time it changes direction, acceleration or force also changes direction, right? And
Yeah.
remains perpendicular. So if you want to find the radius of that circle, you can say that magnitude of the force is equal to QVB and should be causing the centripetal acceleration along the circle. That should be mv square by r. Therefore, you'll get r is equal to mv by qb. This is the radius of the circular path that a charged particle takes if it is placed in a magnetic field, right? It will
Yeah.
turn around like this and it will move like this. Obviously, you have to be careful about vectors and all here in the sense that force is q v cross b. So you should, if it is a slightly complicated situation, you should always write the v vector as whatever it is in terms of I and j, and b vector also in terms of I and j, and do the cross product to realize what the force will be, right?
Yeah.
Now here you can get the direction of the force by doing right hand thumb rule. So if you say right hand thumb rule gives you direction of any A cross B type of vector. So here the A will be your V vector and B will be your magnetic field vector. So the way it is done is right hand thumb rule, you stretch the fingers along the first vector and then curl it along the second vector. And that should give you the direction of the force acting on it, right?
Yeah.
So if the magnetic field in this region was like this dot denotes it is coming out of the plane of the paper, then V is in this direction, the dot, the curl of the finger should be coming out of the plane of the screen, and therefore the thumb will point this way, right?
Yeah.
That is why the force is this way, and that makes it turn in this direction, right?
Yeah.
One thing to notice here is section 34.3, where he explains how electric and magnetic fields are basically interrelated. Electric and magnetic fields are interrelated in a strange way. So actually, like in higher physics, you will realize that magnetism is just a relativistic effect. The effect when you try to integrate relative motion into electrostatics. But you don't need to worry about that right now. He gives a thought experiment here, which helps you understand this connection. So he's saying there is a wire, a current carrying wire, and there's a charge that is moving with velocity v, right? Due to
Yeah.
this current carrying wire, there is a magnetic field in this region, right? Now,
Yeah.
magnetic field in this region will be cross or into the plane, right? Because again, we'll learn later right hand thumb rule. If you stretch the thumb along the direction of the wire, the curl of the fingers gives you the direction of magnetic field in the region around it. So you understand, right? Fingers curl inside here, right?
Yeah.
And on the other side, they will come out. So this direction, magnetic field will be like this,
Yeah.
right? So this direction, it is into the plane of the paper. And now you will see here that V cross B will become this way. Force is this way, right? V is like this. B is into the plane of the paper. So force is right hand thumb rule again, this direction, right?
Yeah.
You are able to apply this right hand thumb rule, right? Because it is
Yeah.
very important to be able to figure out directions using that, right?
Yeah.
Okay, so your force is this way, and this is a typical situation. Here, this long wire is supposed to be electrically neutral. Why? Because charges are flowing in the wire, right? And they are not stopping anywhere. Any charge that crosses a section, comes into a section, will cross that section, right?
Yeah.
So wire is electrically neutral, and you see that the charged particle deviates like this. So you will make a conjecture that the reason it is deviating is because of the magnetic field, right? And the force due to the magnetic field, correct?
Yeah.
On the other hand, if, for example, you are on a cart like this, right? You are on a cart, and that cart is moving at the speed vd, where vd is what? It is drift velocity of electrons. No, actually, no. It is moving with the speed v, which is velocity of the charge, right?
Yeah.
Let's say you are observing the same situations like this, where it is moving with speed v. Now the charge is at rest here, right?
Yeah.
Charge is at rest, and uh, the person here still sees it is attracted towards the wire, right?
Yeah.
Correct. So he can't explain this attraction towards the wire on the basis of B, right? Because according to him, the charge is at rest. Correct.
Yeah.
Force due to magnetic field would have been QV cross B, right?
Yeah.
V is zero according to him, right?
Yeah.
So in this frame, the magnetic field cannot exert any force on the charge. However, the observer here still sees that the charge is attracted, is going towards this, right?
Yeah.
Hence, in this field, in this frame, he must say that, okay, the only other thing that can exert a force on a charge is an electric field, right?
Yeah.
So there must be some electric field in this frame from this person's perspective, right? So which is what is pulling the charge towards the wire, right?
Yeah.
We don't want to figure out how electric field is generated in this case. We just want to think about this fact and realize that from a ground frame, something that was a magnetic field is looking like an electric field from this moving frame, right?
Yeah.
So basically, the electric and magnetic fields are different ways of looking at some combined thing. Sometimes you see electric field, sometimes you see magnetic field, and it's called an electromagnetic field. There are two aspects of the same entity, right? Whether the electromagnetic field will show up as an electric field or a magnetic field or a combination depends on the frame from which we are looking at the field. Makes sense?
Yeah.
So if you are confined to a specific frame, if your question is only about some ground frame situation, then you can think of them as separate. But if you are switching between different frames, then one of them might become the other, right?
Yeah.
That is what is explained in this section. And this is important to realize that they are different ways of looking at the same electromagnetic field. The next section is about this motion of charged particle in a uniform field. That is obvious, we discussed it. R becomes mv by qb if it is going in a circular motion. And the time taken to cover a full circle, if you are moving only under the influence of magnetic field, would be T is equal to 2 pi m by qb. And how does it come? It comes because you know that the speed v remains constant, right?
Yeah. Distance by time.
So you'll say 2 pi r by v, right? That is your time period, and r you'll put as mv by qb, right? So
Yeah.
once you get the time period, you can say frequency of motion around the circle will be 1 by time period, which will be qb by 2 pi f, right?
Yeah.
This is in the situation when the velocity and the b were mutually perpendicular. Mutually perpendicular. So this might have been, say, I and this was J. So your force was in K. Force was K, right?
Yeah.
Something like that, right? But it is not necessary that always the velocity of the body will be perpendicular to the magnetic field, right?
Yeah.
It is not necessary. So it might be that, okay, a particle is moving with a velocity that is having two components. One is Vy and one is Vx, right? Correct.
Yeah.
And magnetic field in this region was like this in this direction. B was in I cap, right? So
Yeah.
actually the particle is moving like this. And you can see that it has one component along the magnetic field and one component perpendicular to it, right?
Yeah.
Now, when you do Q V cross B here, the only component that matters in the force due to magnetic field will be the component that is perpendicular to it, right? Because you
Yeah.
say Vy j cap cross B I cap. Vx I cap cross I cap becomes 0, right?
Yeah.
And the force will become minus Q Vy B K cap, right?
Yeah.
So notice that the force is not in the xy plane, it is still in the z plane. Z plane is like this, right?
Yeah.
So force is pushing the particle inside like this in a circle on the z plane like this, right?
Yeah.
If there was 0 Vx, we would have said it will go in a circle like this on the z axis, right?
Yeah.
But we can't ignore the Vx. The Vy part is there to create a force like this, but Vx is still there, right?
Yeah.
The particle still moves forward, correct?
Yeah.
So the particle moves in a spiral now. Spiral now because it is a circle that where the particle is moving ahead also, right? Correct.
Yeah.
The motion ahead is because of the Vx. The motion in the circle is because of the perpendicular component of velocity. Velocity component that was perpendicular to the B, right?
Yeah.
So radius of the circle will be due to the perpendicular component m Vy by qb, right?
Yeah.
And therefore, time period will still be 2 pi m by qb. And once you have the time period, you will realize that in each rotation, the particle will move ahead by some distance, right?
Yeah.
So that is called the pitch of the helix. That pitch of the helix becomes this time period into the velocity in the x direction, right? So Vx into 2 pi m by qb. That becomes your pitch. Understand?
Yeah.
So that is your helical motion due to this. Now we'll do an extension of this QV cross B force. So if you have a current carrying wire, for example, wire carries current I, and let's say the wire was placed in a magnetic field. Placed in a magnetic field. Let's say B is the magnetic field in this whole region. So we know from current electricity that I is equal to NEAVD, right?
Yeah.
Where N is number of electrons per unit volume, E is charge, A is area of cross section, VD is drift velocity, right?
Yeah.
Now, if you take a small section of the wire, let's say DL length of the wire, the charge in this DL length would be how much? It would be ADL is the volume and multiplied by N, right?
Yeah.
Correct. This is the
Yeah.
charge, and this charge is moving at speed VD, right?
Yeah.
So force dF on this small section of the wire due to magnetic field would be Q dQ and VD cross B, right?
Yeah.
And dQ is NADL VD cross B, right?
Yeah.
Right. Now, what you can do here, wait, this is just the count. You have to multiply by E also, right? For charge. This is the number of particles. No? You have to
Yeah.
multiply by electrons charge, right? To get dq,
Yeah.
right? So what you can do now is dl vector. You have to realize that dl vector and vd vector will have same direction. So you can interchange their magnitudes, right?
Yeah.
Like suppose vd was some 10 I cap and dl was some 0.1 I cap. Since they have same direction, you can put 0.1 inside and take 10 outside, right?
Yeah.
Because they are in the same direction. So I'll say ENAVD magnitude and DL cross B, right?
Yeah.
And this part is called your current, NEAVD, right?
Yeah.
So the force becomes I DL cross B on a small section of the wire, right?
Yeah.
So on a small section of the wire, make the direction of your DL is something in the direction of the current. DL direction is always in the direction of the current, and your DF on this becomes IDL cross B. And if I want to find the total force on the whole thing, I will have to add all such DFs, right?
Yeah.
So you will have to integrate IDL cross B to get the total force F on a current carrying wire due to magnetic field, right?
Yeah.
If DL cross B is simple, you can just, and B is constant, let's say, over all the wire elements, you can take it outside and do integral DL. So it might sometimes look like if it is a uniform current carrying wire and field is also constant, it might become just IL cross B sometimes after integrating, right?
Yeah.
So that is your force on a current carrying wire. Now, because of this force on a current carrying wire, you will have a situation where there will be torque on a current carrying loop also. So you can take a current carrying loop like this. This is 34.6. And obviously every part, every side has a current. And if it is in some magnetic field, let's say dot magnetic field here. Right now, when it is perpendicular to the magnetic field, this plane, this square loop is in the plane which is perpendicular to B. In that situation, since the squares have equal sides, forces will be such that they will cancel out, right?
Yeah.
Because direction of current is reversed in the opposite way. No? So force will be downward here, then it will be upward here. And similarly here also, right?
Yeah.
So total forces will be zero in this situation. And torque will also be zero. because the forces are passing through the axis. There is no torque due to these forces about the central axis, right?
Yeah.
However, if you rotate it slightly, rotate the loop slightly so that this central axis and this makes 30 degrees or some theta, right? In that case, what will happen? You will realize that forces are still equal, but now they are not directly opposite to each other, right? Like you have to think of it in 3D. This power portion is coming out towards you, this portion is behind, right?
Yeah.
And these portions are still the same. So
Yeah.
you will see that forces are still balanced. If you take all the net forces, it will still be equal. But the point is that the line of action of the forces is not the same, right?
Yeah.
Line of action of forces is different because one of them is acting on this wire which is behind the plane and this is ahead of the plane, right?
Yeah.
So if that is the situation, this causes a torque about the central line, right?
Yeah.
And this also causes a torque about this, and both the torques will add, correct?
Yeah.
If you think about it three-dimensionally, then you will understand that the torques will add. Okay.
Yeah.
So in this derivation here, what he has done is just calculated the torque due to that line R dash S dash and torque due to P dash Q dash. Forces are acting there, those two lines, and he finds the torque there. So torque will be R cross F, right?
Yeah.
So torque about the central point would be the R vector from the central line, the axis line, to the point where the force is acting. So your R vectors will be like this. This is your R vector, this is your F vector. And similarly, this is your R vector, this is your F vector, right?
Yeah.
So when you take the magnitude R cross F, when you do, then obviously you will take angle between these two, right?
Yeah.
So it will be sine theta and all, and eventually you will get IAB sine theta is the total torque after adding this component and this component. You should go through that calculation there. He has explained it, right?
Yeah.
Force was ILB and B by 2 sine theta is because of the R cross F. If this length is B by 2, right?
Yeah.
B by 2 cross ILB sine theta. And similarly here it gets added and becomes this, where A is the area of the loop and B is the magnetic field and theta is the direction between the area vector and the magnetic field. Okay.
Yeah.
A is the area of the loop. This can also be written as I cross, no, this can be written as mu cross B, where mu is defined as magnetic moment of the loop. Magnetic moment, which is basically just a way of saying I into A. And if there are multiple loops, you'll say NIA, right?
Yeah.
Magnetic moment vector is always going to be in the direction of the area vector, in area vector's direction, and area vector direction is always perpendicular to the surface, right?
Yeah.
So if you find your magnetic moment, then you have a simple formula to calculate the torque on a loop. It is mu cross B, right?
Yeah.
This is similar to what happened in case of electric dipoles where torque was P cross E, right?
Yeah.
And P was the electric dipole moment, which was simply Q into D, right?
Yeah.
Again, B vector had a direction, E vector had a direction. That is why we are defining it like this. We could have left it here, but we are defining something called IA as mu in order to be able to write it like this. Because now we can see parallels between electric torque on a dipole and magnetic torque due to magnetic force on a current carrying coil, which is a magnetic dipole, right?
Yeah.
Okay. This chapter theory is this much only. Like obviously you'll have to practice some questions, especially like do the examples a little bit. Example number 9, 10 and 11 are super important. 10, 11. Make sure that you go through 10, 11 and also question number. I mean, there are nice questions in this exercise, but definitely question number 51. Several other questions are actually before 43 and all. There are many questions that you should look at.
I had started doing the exercise.
If you have doubts, you can tell me.
Yeah, like I had marked question 13,
Hmm.
15,
Hmm.
21st, 25th, the B part, and I had only finished till 40, so nothing after that.
13, 15, 21st,
And
20.
25th part B.
Okay. So 13, for example, let's look at that. A hypothetical magnetic field exists in a region. Okay. So first draw this situation. So magnetic field exists in a region where B is given by B naught ER vector. ER vector is unit vector along the radial direction, right?
Yeah.
A circular loop of radius A is placed with its plane parallel to xy plane. Center is at 0, 0, D. Let's say this point is 0, 0, D. You have a circular loop here, right?
Yeah.
0, 0, D. And its radius is A. Radius is A, right?
Yeah.
Now, this is your X, this is your Y, and this is your Z. And magnetic field is radial in direction. Radial direction means what? It means that from the origin to the point, right?
Yeah.
Let's say this is a point P. This is your radial direction, ER, right?
Yeah.
Magnetic field is always like this, in this radial direction, correct?
Yeah.
So what we want to find the magnitude of magnetic force acting on the loop, right?
Yeah.
So technically what you have to do is each portion of the loop I dl cross B you have to do, and then that is your df, and then you have to integrate this, right?
Yeah.
I dl cross B you have to integrate, then you will get the answer, right?
Yeah.
Now, how do we do this? The problem is that the loop is not at the origin and all, loop is at a place like this. We have to write your dl vector on the loop, and also we have to write the B vector there, right?
Yeah.
So it's a little annoying, but it's not like difficult to do. Like, for example, okay, I'll just draw a different figure. We'll do it from there. So, if you have situation like this where your center is 0, 0, D and radius is something, right? Any arbitrary point here, right?
Yeah.
It has radius A, correct?
Yeah.
And you can find the coordinates of that point because the point will be, let's say, A cos theta, A sin theta, comma D, right?
Yeah.
Because it is parallel to the XY plane, right?
Yeah.
And your theta varies from 0 to 2 pi, right?
Yeah.
If it was in XY plane, you would have just written A cos theta, A sin theta 0, right?
Yeah.
So this is an arbitrary element here, okay? And this is the position of that element. The DL is at this point, right?
Yeah.
You have to write the DL vector also, and you have to write the R vector also. R vector will be line joining this to the origin, right?
Yeah.
So R vector is simple. It is A cos theta I cap plus A sin theta j cap plus D k cap, right?
Yeah.
Because that is the point where we are placing our DL, right?
Yeah.
Now, what about the DL vector's direction? So let's say if we have a circle like this, and you are at angle theta like this. DL is along the tangent, right? Right?
Yeah.
Correct?
Yeah.
So DL is along the tangent. So DL vector would be the tangential vector. We can easily write it. This length is AD theta, right? Length is
Yeah.
AD theta because I will take a small element like this, right?
Yeah.
Magnitude of DL is this. Direction is, it is positive x. So it will be, if this is theta, this is theta 90 minus theta. So cos 90 minus sine theta, right?
Yeah.
Sine theta I cap minus cos theta j cap, right?
Yeah.
This is your DL vector, no?
Yeah.
Makes sense.
Yeah.
So even if you are placing it at 0, 0, D center, still your DL vector will be something like that. No?
Yeah.
DL vector cannot be perpendicular. It cannot be having any component in K because it is in the plane of the circle, right?
Yeah.
Are you understanding?
Yeah.
It is in the plane of the circle and circle is parallel to XY plane. So this is your DL vector. So now let's just do DL cross B naught ER, right? So
Yeah.
DL and R vector I already know. So B naught will come out. And when you do DL cross, let's do that calculation. So this cross, this is 0. I cross J will have something, right?
Yeah.
You'll get A square sine square theta d theta. I cross J is K, right?
Yeah.
And I cross K will be something. So you'll get AD sine theta d theta, and I cross K would be minus J, right?
Yeah.
This minus A cos theta d theta with this J cross I. So minus A square cos square theta d theta, and J cross I would be minus K, right?
Yeah.
And lastly, this with the last term. So minus A d theta cos theta minus A d cos theta d theta. J cross K would be
Okay.
I cap, right?
Yeah.
So these are my, this is my resultant after the cross product, right?
Yeah.
And there will be a B naught outside. And what was the current in that wire? Current is I. So I B naught and all come out, right?
Yeah.
I B naught comes out, and this is the integral, and I have to integrate from 0 to 2 pi for theta, right?
Yeah.
So notice that this integral vanishes because sine theta over 0 to 2 pi will be 0, right?
Yeah.
And cos theta over 0 to 2 pi will also be 0, right?
Yeah.
So these two will not matter. What will matter is this part, right?
Yeah.
Correct.
Yeah.
So, okay, so this can be, first of all, it can be simplified. You can take A square. Notice the sine square plus cos square it will become, right?
Yeah.
So it is just A square d theta, right?
Yeah.
In the K cap, right?
Yeah.
So 2 pi A square will come into I B naught, right?
Yeah.
So that will be your total force. 2 pi A square I B naught. Should check that.
It's given divided by root over a square plus d square.
1 second, then I have made some mistake somewhere. Oh wait, I made a mistake because I did not take it as a unit vector. No? What is the length of this unit vector? Right?
Yeah. It
This
would be a
was
square
A
plus d
square
square.
plus D square, right?
Yeah.
So this unit vector, if you account for, you will get a denominator stuff also, right?
Yeah.
Makes sense.
Yeah.
So basically what we are doing is just simply writing DL, writing B. It takes a little bit of patience to figure it out, but it is possible to do that, DL and B. Once you do that, you have to integrate to cover the whole thing, right?
Yeah.
That is your 13th one. Then 15th one. Current loop of arbitrary shape lies in a uniform magnetic field. Show that the net magnetic force acting on the loop is zero. So arbitrary shape current loop is in a uniform magnetic field. B is constant, right?
Yeah.
Show that the net magnetic force on the loop is zero. So any portion you have a DL force here, DF would be I
DL
DL
cross.
cross P. And when you integrate, you have to integrate over the whole loop. So you'll do integral of I DL cross B. Now, because magnetic field is constant, right? The
Yeah.
B is a constant here, right?
Yeah.
So what will happen is B can be arbitrary direction. Every B is constant. So all the time it is like this every place, right?
Yeah.
So I will come out, B will come out, and it will just be integral of DL sine theta, right?
Yeah.
Where DL sine theta, theta is the angle between this and this, right? So
Yeah.
DL sine theta would be perpendicular to the B direction, right?
Yeah.
Perpendicular to the B direction everywhere. Technically, what we are saying is integral of DL around the closed loop will be zero, right?
Yeah.
Like if you go around a closed loop, no matter what the shape is, the vectors have to add up to zero, no?
Yeah.
Otherwise, the loop will never be closed, right?
Yeah.
So one way to think about this is just write it as I DL1 B cross B, right?
Yeah.
And add IDL2 cross B, right? So technically it can be written as I DL1 plus DL2 and so on cross B, right?
Yeah.
Because when you do vector addition is associative. So if you have A1 cross B plus A2 cross B, all are vectors, then you can say A1 plus A2 cross B, right?
Yeah.
Don't remove sine theta now, that just confuses everything. Just write it like this and say that ultimately it is some of these vectors cross B, right?
Yeah.
Because B is anyway constant. And some of these vectors has to be zero because it is a closed loop. No matter
Yeah.
what shape it is, sum of all the vectors has to add up to zero, right?
Yeah.
So therefore, if it is a uniform magnetic field, the force on a arbitrary shape current carrying wire will still be zero, right?
Yeah.
Understood, no?
Yeah.
And which one? 21.
Yeah. 21.
Shows a rod PQ of length 20 suspended like this through fixed point by two threads. A magnetic field of 0.5 Tesla exists in the vicinity of this region. Okay. Wire extending PQ with wires connecting PQ with the battery are loose. Okay. Okay. Carry no tension and exert no force on PQ. Okay. Find the tension in the threads when the switch is open. When the switch is open, tension in the threads are the ones that suspend it, right?
Yeah.
So that is an easy part, right?
Yeah.
You should get the answer for part A, no problem, right?
Yeah.
Okay, so a current is now established when switch S is closed. Tension is what now? When current is established, PQ section of the wire has a current like this, and magnetic field is given as shown in the figure 0.5, it is dot. So it is 0.5 k cap, right?
Yeah.
B is this, wire has an I cap direction, right?
Yeah.
So force on the PQ section of the wire, right, would be IL cross B. So 2 into L is, this is 20 centimeter, 20 centimeter. Okay, so 20 centimeters. So zero point 0.2 I cap cross 0.5 K cap, right?
Yeah.
So this will become K cross I is J. So this is minus J. So it becomes minus, this is 2 by
0.5.
10 and 5 by 10. So 10 by 100, 1 by 10, right?
Yeah.
Minus 0.2 J, right?
Yeah.
So minus J means downward force on this wire, right?
Yeah.
So, okay. Now you do the equilibrium. You have a downward force on the wire PQ and upward forces you to tension, right?
Yeah.
And mass of the rod, right?
Yeah.
Balance everything, you should get the answer, right?
Yeah. I think so.
This is 60, this is 30. So you'll say T cos 30 upward. So 2T cos 30. 2T cos 30 should be equal to 0.2 plus mass, whatever it is, weight. So 200, so 2 by 10 into 10, right?
Yeah.
So it is 2.2 is equal to 2T cos 30. So T will be 2.2 by 2 into cos 30 is root 3 by 2. So 4 by root 3, roughly. So check what is coming. Question number 21. 4 by root 3 is saying 1.25, that is.
4 by root 3 is 2.309.
Something is wrong. 1 second. I've been missing something. Fixed point by 2 threads, magnetic field, wires connecting a loop. First answer you got.
Yeah, I got it as 2 by root 3.
2 by root 3 is how much? 1 point something.
1.13.
Okay, so first answer you got, then that time you just not including this, right? It's the same thing. 2T cos 30 is mg, right?
Yeah, so I think,
Correct. So that would give you
yeah.
2 by root 3. So now we just have to see what happens because of the wire present. Force is downward only.
I think it's because we took G as 10.
No, that will not change it so much. That shouldn't change it so much. No, it is much higher right now. 0.5 Tesla. Maybe our calculation here for force and all is wrong. Just check this. IDL cross P 2 ampere. Length is 20 centimeter. 0.2 I cross 0.5. So this becomes half into, this becomes 2 by 10. So 1 by 10. So 0.2. 0.2 is correct. And there we have mass 200 gram. Okay. So 2.2 is coming downward force.
Yeah, I did the calculations again. I got it as 1.247 this time.
What calculations?
So 2 2t cos 30 is equal to 0.2 into 9.8 plus 0.2 into j cap. So that approximately comes up as 2.16.
This is the weight, and then we had, oh wait, we are making a mistake. No. How did we get 2.2 here? Okay, it's fine. So this is fine, I think. This
Yes,
is
it comes as 2.16, and then cos 30 is root 3 by 2. So divide by root 3.
1.7. Okay, it's fine only, right?
Yeah.
Yeah. Uh, yeah, fine. 25th. Okay, so 25th is a slightly weird one. I mean, 25th is fine, I think. But I know this is slightly weird. Shows a circular wire loop of radius A carrying current I placed in a perpendicular magnetic field. Consider a small part of the wire, right?
Yeah.
So small part dl of the wire, let's say dl. Find the force on this part of the wire exerted by the magnetic field. That is easy. Force
Yes.
would be I dl cross B, and dl is always perpendicular, so it's IDLB, right?
Yeah.
Find the force of compression in the wire, right?
Yeah.
So force due to this, let's say dl vector was like this, and dl vector was like this, then I dl cross B is in what direction? Dl minus I cap cross B is in minus k cap. So I cross k, k
Minus
cross I
K.
is j, so this is minus j, right? So
Yeah.
minus TL B j cap, right?
Yeah.
This is like this. So this is a downward force on it, right?
Yeah.
Calculate the force of compression in the wire. Okay.
Why will the wire compress? Won't it like just move or something?
No, net force on the wire is zero. No? We just now proved in question 21. If there is a uniform force, uniform field, what happens to any arbitrary shape?
Okay, yeah, the net force
Net
is
force
zero.
due to magnetic field is zero. However, at every point, there is an internal force, right? So force of compression, he's asking. Wire loop of radius A. The question is a matter of understanding what he means by this force of compression. So, okay, IDLP, that is the force. And if you, let's say tension in the wire is something, TT for this section, right?
Yeah.
This is a tiny section. This kind of derivation you would have seen already. This is 2d theta, or d theta. So d theta by 2 is this angle, right? So you
Yeah.
can say t sine d theta by 2 is this component and this component. So you say 2t sine d theta by 2 should be equal to IDLB, because because of this compression force only the tension is coming, right?
Yeah.
Like otherwise, if you just keep the wire and no magnetic field, then tension is zero, right?
Yeah.
If there is nothing there, then tension would have been zero. Tension has arisen because of the magnetic force, right?
Yeah.
So we can say T d theta, right, is equal to IDLB, right?
Yeah.
The sine d theta by 2 is d theta by 2. So if I integrate both sides here, right, to cover the whole wire, right,
Yeah.
I will get T into 2 pi is equal to I into 2 pi AB,
Yeah.
right? And 2 pi will cancel and tension is coming out to be IAB, right?
Yeah.
That is, I think, what he means by the force of compression in the wire. Like, force of compression in the wire means what is the tension generated in the wire due to this magnetic field. So this type of derivation you have seen, right? This whole thing. There's a circular loop, there's tension. This angle will be d theta by 2, right?
Yeah.
This whole angle is d theta. And tension has two components, two components like this downwards. Those are because of this. We equate those and integrate. So you'll get tension like this. Makes sense?
Yeah.
I mean, this is fine. The next one will be slightly more difficult, I think. You should try that, 26. Also, go through the examples a little bit and try the remaining questions. We'll finish the next chapter in the next class. So you can go through 35 also, right?
Yeah.
We'll do that next.
Okay.
Okay, that's all for now. We'll see you.
Thank you.